โทษนะคะวิทยากรใช่ไหมคะขออนุญาตติดไมค์
โอเคอ้าวเดี๋ยวผมขอลองเอาอันนี้ออกนะเดี๋ยวไม่แน่ใจไหมเดี๋ยวติดเดี๋ยวดับงงเดี๋ยวขอแป๊บนึงนะผมขอไปเสียบโอเคได้ละอ้าว
ไม่มันไอตัวการ์ดจอมันเหมือนบอกไว้ SDCP เสร็จแล้ว
จังได้แล้วได้ครับ
อันนี้เลเซอร์
อันนี้พอยเตอร์จะเป็นเลสเอาต้องออนก่อนโอเคได้แล้วครับแต่เลเซอร์เหมือนจะไม่ติดออกขึ้นจอไม่ได้เอางั้นโอเคงั้นที่จริงไม่ต้องก็ได้ครับถ้ายิงขึ้นเวทีทีวีไม่ได้ไม่ต้องก็ได้เดี๋ยวผมกดตรงคอมเมาส์ก็ได้เพราะว่ายังไงก็ต้องโค้ดอยู่แล้วตอนแรกนึกว่าจะใช้พอยต์อะไรแต่ไม่เป็นไรก็ได้ครับ
All right. Please gather up at the launch pad. Please gather up at the launch pad. Our next session will begin shortly.
ไม่มีครับ
This session is designed towards the track number 1. It will be about the navigating the world of transformers, modern language models, fine-tuning, and the magic of prompting in NLP. So everyone, please give a big round of applause to คุณชมปกรณ์ ชมปกรณ์จันแสงชัยโชติ from Wistech ครับ
Okay, so good afternoon, everyone. My name is Chan. So AKA sometimes people call me Chong. So feel free to call me whatever you like. I'm here in the behalf of like Ajahn Sarana Nutanong. So he is at Wistech right now. So a little bit about myself here. I'm a senior data scientist at Visai AI. So we're a partner with SCP 10X as well. I'm experienced in working on NLP. So fun fact. Ajahn Sarana is also my co-advisor for my master degrees. So yeah, I was here in the behalf of like him presenting at Wistech as well. So today I'll go for a brief introduction about how we can fine-tuning the models and how can we use prompting to solve the same problems. The outline is kind of like straightforward, but I'll try to keep it within 1 hour if I can. All right, so there's gonna a lot of codings today. So is anyone here have notebook with yourself right now? I'll suggest like have at least 2 notebooks per group because like we're gonna use to collab session. Okay, so like
So maybe a few minutes, 1 minute to grab your notebook because this will be pretty much hands-on.
Yeah,
workshop.
hands-on.
How might we improve LLM for low resource language?
Okay, so before I start, did everybody here participating in matching day? Or like, did anyone miss the matching day?
Who was here on the matching day?
Okay, great. So, because like today workshop is gonna be like an extension towards that talk. Because like we're gonna skip most of the slides because like we're trying to focus on a hands-on workshop. But before we start again, another question. Did any of you like are familiar with encoder decoder transformer based model? Like, or like if I have no idea what is transformer encoder decoder is like, is there anybody not familiar with transformer? Prompting? Someone new here to prompting in context learning? All right, perfect. So I think everybody's here is on the right track. Because like today is going to be very technical, and I'm trying to like fit everything within a 1 hour also. Okay, so anybody here have Colab Pro? If you have Colab Pro, you can finish it. You can do the workshop in with one notebook. Okay, so I would suggest have at least 2 Colab sessions because like one Google account can open more than 1 GPU session. So it's better to have 2 notebooks opening different Colab session. All right. Okay, so let's get started. So the task for track 1 is going to be like Kaggle-based competition. In this workshop, we're going to do the same. We're going to go through on how can we fine-tune the text classification model, as well as token classification, or what we sometimes call name entity recognition task. We're gonna give you a tutorial for both supervised fine-tuning on the encoder-based model, like for example, Wangchan Roberta, XLM Roberta, sorry, so on and so forth. And we're also gonna give you a tutorial on how to supervise fine-tune the token classification task on encoder-based model as well. But not only will I gonna go through you on how to like do supervised fine-tuning, I'm gonna tell you how to do it with the transformer decoder-based model via in-context learning as well. Right? So on track 1, so the challenge is how might we improve LLM for low resource language, right? So we're going to benchmark it on 2 tasks, like what I mentioned before, text classification and NER. If you can actually train the decoder-based model using in-context learning to beat the encoder-based model, so that's going to be very good. But you're free to choose any choice. Either you're going to choose encoder or decoder-based model, it's up to you. So this workshop is going to go through you guys on how can we fine-tune and apply in-context learning. Anybody here have used Wangchan Berta to fine-tune text classification or NER before? Okay, just one. So okay, I'll go through the supervised fine-tuning first. Okay, so for the URL, you can go through the tinyurl.com/AIHackathon 2023-SFT for supervised fine-tuning. And the second person who have the collab with them, the notebook with them, you can open the second link here. ICL refers to in-context learning. So the first one is the notebook for supervised fine-tuning, and the second one is the notebook for in-context learning. Right. Okay, so once you open the collab, you're gonna see 2 collabs, just like this. Okay, so a little bit of remark for this workshop. Although the session is in English, we're more than welcome to have a question, especially in Thai, because like I'm afraid that we might have some miscommunication if you kind of like use too much English. So ถ้ามีคำถามภาษาไทยก็ยินดีนะครับหรือว่าถ้าติดตรงไหนเบรกได้ตลอดเลยเพราะว่ามันจะน่าเบื่อนิดนึงเหมือนเลคเชอร์แต่ว่ามันเป็นสิ่งที่จำเป็นสำหรับแทร็ก1เนาะนะครับ Okay, so I want to emphasize again. So if you have any questions towards this workshop, please feel free to stop me anytime and ask me some questions because like this part is going to be crucial for you to to run the experiment and submit the benchmark on the competition day. All right. Okay, so everybody has the Colabs open right now, right? Is anybody have some issue with Colabs? All right, cool. So before we start, the person who's opening the Colab for the in-context learning, make sure you have the GPU with you. Oh, sorry, I forgot to stop the presentation. Okay, that's better. Okay, so for those who are using the Colab, don't forget to copy the notebook to your drive, or else any change applied to your codes won't be saved. Okay, make sure you copy it to your own drive, and you make a copy so that whenever you take a note or you modify some codes, it changes in your Google Drive, not mine. All right. Okay. So first thing is that to make sure you have the GPU ready. And then install some dependencies. So default Colab doesn't have these following packages. So we need to install them first. Then we move to the initialize model part. This one is going to take a long time, around like 10 minutes or so, because we are downloading 7 billion models. Okay, so before we start, make sure to download these model first. So we're using the Wangchang LM model. You can feel free to use other model in the future, but for this demo, we're going to use the Wangchang LM just for this workshop. So in case you're in a hackathon and you want to build your own, let's say like your own model, you feel free to choose to change this model, but make sure that if you change the model, the codes, everything like below this part, make sure you adapt it so that it's also suitable with your models as well. Okay, so the first thing you need to do is download the model. It took around like 10 to 20 minutes or so. Then we back to this Colab. Let me change the users first. This one's fine. Okay, so back to the supervised fine-tuning notebook. Again, make sure to copy it into your drive to make sure that any change is applied. Okay, so while the model is downloading on the in-context learning notebook, I'll go through how to supervise fine-tuning the encoder-based model on text classification tasks first. So again, make sure you have some GPU available on your runtime, or else everything is going to be too slow. Okay. Anybody have issue with checking the GPU? All right, perfect. So again, we need to install the dependencies, right? Because we are downloading the models. We're going to install some dependency first. Okay, so once we finish install the libraries, the first thing we need to do is to import the necessary modules that we have installed. So this one is straightforward. Another thing that we need to keep in mind is that in this workshop, we are using the Wangchang Berta, and Wangchang Berta have a specific pre-processing function. So if you're fine-tuning the Wangchang Berta model, just Wangchang Berta, you need to make sure you pre-process the same way as it's pre-trained, so that the text distribution won't skew that much. So I actually give you the code to download the pre-processing scripts. Is available on this GitHub repository. So with you running the debugget here, it will download it to the local file, and you can import it to use it later. All right. Okay, so before we start with preparing the data set, I'll define the evaluation function, because like whenever we're training, we want to monitor if the model is like not overfitting. Every time we're training, we're going to evaluate with the validation set. So we define the evaluation function, that we will return the accuracy, F1 precision, and recall whenever we are training. So this is just the function that we predefined, and we will use it later on. Okay. Okay, now to the fun part, the fine-tuning part. Okay. The first thing is that we define the parameters of the training. So we're going to use the Wang-Chan Berta, as I mentioned. You can feel free to change this later on, but don't change this now because like some pre-processing function that we apply here doesn't apply with the XLM raw database. So for this workshop, I'm going to use the Wang-Chan Berta with the dataset white size sentiment. We predefine that the feature column that we're going to use to apply the text classification, the feature column is text, labels, category, output, batch size, learning rate, and epoch, so on and so forth. Okay, so we start with defining the arguments of the training function. Then we download the dataset using the Hugging Face. All right, so the first line here is to download the dataset that are publicly available on the Hugging Face Hub. The second one here is to do the symbol pre-processing. So we're going to assign we are going to convert the labels column category into labels. And then we're going to get the unique labels here. So if we inspect the download data, you can see that we already got splits of train, validation, and test set. Just like white side already split into 3 parts already. You can see there's like around like 20K also text for sentiment here. Let's look at num labels. So there's 4 labels here for the text classification task. You can actually investigate the data set by checking the train here. You can see that the training data have 4 columns. Oops, sorry, misspelled. Name, text, and labels. If you investigate the first index here, you can see that the first data point is the text. So it's the product review, or kind of like the random text scrape from the online here, from the white sites, and its corresponding labels. So the 0, 1, 2, 3, 4, it's a label. But before we convert this text here, we need to pre-process the input text first, right? Because as I mentioned that when Wang-Chan Berta was pre-trained, it was pre-processed by a specific function so that it's more suitable to Thai language. So we're going to define a pre-process function to pre-process every text in the dataset. So like in previous example, we have used map function to apply the pre-processing function to every training example, as well as validation and test set. All right, so this could take a while. So this here, the progress bar shows the progress for mapping the function between training, validation, and test. So once we finish pre-processing, we are enough with the pre-processed text. You can see here that there's not much difference. The only difference is that it casts to lowercase and all space is converted into the spatial space token. Can anyone guess what is the role for this spatial space token? It's going to be too technical question here. Can anybody here guess? Okay, so Wang-Chan Berta is using a sentence piece model. It's engineered based on English language, where it's going to require some special tokens to specify the first word of the character. Like for example, if I say I am 10, the default tokenizer is going to be I am and 10. See here, this token here indicates that it's the first letter, is the first word that following the space here. But the problem is that Thai language wasn't engineered this way. Every space matters in Thai. It's like, you know what it's mean to read the Thai character without space, right? Space actually has some meanings in Thai. So we got to engineer so that it doesn't ignore the space token. All right, so it's kind of a quick hack. If you want some more info on how Wang-Chan Berta was pre-processing, feel free to refer to this paper here. All right, I don't recommend you to read all the papers, it's too long. I would suggest you reading to kind of like how they pre-process the data, how they engineer with the pre-processing step to make sure that it's more compatible with Thai language. Okay, cool. So we have pre-processed the data, but the next step here is to encode the data. What does encode mean? We know that language doesn't read, right? So we can somehow say that language, like the AI somehow understanding the language, but actually we gotta somehow pre-process every text data into numbers anyway. So the function encodes or tokenizer here, the goal is to convert every text data into a list of word or subword, I per se, and then we encode it into the index number. So let's say we apply the tokenization here, and then let's inspect the encoded data set. What is it? How is it different from the current data? Okay, while it's loading. Okay, it's downloading faster than I expected, and that's a good thing. Because like yesterday, Aaron, it took me around like 30 minutes or so to download the 7 billion models. Okay, so you can see here that when I apply the encoded function, the raw text here, which should be string, right? It converts into a list of integers. So each integer represents each subword. You can see here, input ID is encoded text, right? And if we inspect it later, if I apply the function convert IDs to tokens, you can see how each token was represented. So you can see here, ไปจองมาแล้วนะจ๊ะ right? It tokenized into ไปจองมาแล้วนะจ๊ะ. You can see here, this one is representing the start of a sentence. ไป is the first word, จองมาแล้วนะจ๊ะ, and then space word, space token here. Okay, so this is the idea of how encoder-based model or any transformer-based model understand the language. It maps the token, the string, tokenize it, and then map into the list of token. But you can see here, that's a pad token, right? The problem with transformer is that it only accepts a certain amount of sequence length. For example, here, the maximum sequence length of function beta is 510, not 12, 510. It needs to pass the data to make sure that the sequence length was consumed up to 510. Because like we specified back here that we want to pad into the math length, which is like 510 that we defined during the arguments part. Okay, so once we prepare the data, we have the data set, right? Which contains the input IDs. That is the index of each token. We have the attention mask. Attention mask is whether the index of the token is not a padded token. You can see here that there's a majority one here, and those one are corresponding to 0, meaning that we want the model to ignore all the padded token. Okay, cool. So once we have prepared the data set, the next step is to define the model. The very good thing about using the encoder-based model is that Hugging Face already has every model you can do to finish it within like 10 minutes or so. You don't need to define the class model if you like learn the deep learning course before. With Hugging Face, you can use auto model for sequence classification from pre-train, and then we use the model name Wang-Chan Berta, specify the number of labels, which is 4, and boom, we got the model. This function here automatically loads the pre-trained model that we defined, which in this case is the Wang-Chan Berta, and then they're going to attach the classifier to the model. This way, we have the model that are able to do the text classification prediction with 4 classes. As simple as that. Okay, so then we define the training arguments, the parameter for training. We want the model to save at the output directory that we specify, use a certain learning range, batch size, epochs. We want a little bit of warm up here. So we warm up around like 10% or so if I can remember the arguments correctly. We add some weight decays, save the model, seed. But for this workshop, I want train for a full 5 epochs, or else the workshop won't be finished within 1 hour, right? So for this workshop, I'm going to train for just 50 steps, and then log every 5 steps here. Then we define a trainer function that we use the encoded dataset as a training data, encoded validation as a validation data, define the tokenization, and the evaluation function that we just defined earlier, and boom, we can start training the model right away. As simple as that. Okay. So during the training, I'm going to switch back to the in-context learning here. Anybody here haven't finished downloading the model for the in-context learning? Raise your hand. Okay, I'll wait for you guys to finish downloading first. it could take a while. Okay. So you can see here that it's very easy to train the encoder model with Hugging Face APIs, libraries, with simple like declaration of what hyperparameter to use, mapping function, datasets, and then you can easily use the model. The most important thing I want to remind you with when experimenting with these stuff is that make sure you pre-process everything correctly. You can craft a base model in the market. You can use the base state-of-the-art model, but if you pre-process it incorrectly, it could be worse than the baseline. So just to make sure that you pre-process it correctly. The very bad thing about being a data scientist is that your codes can run smoothly, your training step can run perfectly, but you're gonna take some time to find which part of the code that you're doing wrong. Because like the loss is going down, the metric is going down, it's going great, but it's not good enough. Like I remember one time I forgot to cast the pre-processing function and thing doesn't work as correctly. It took me around like 2 to 3 days to figure out I forgot to replace the special token ID or something like that. So don't make this silly mistake like me. Okay, because it's kind of like it's very hard to find the errors with the data science course, especially in the part where it can run despite a very bad input. So make sure that you make the input correct, right? So before you move on here, you can see here that I declare the parameter set that I want to evaluate every 25 steps, all right? So you can see here that once it completed 25 steps, it evaluates the results of my model. So it tells me what does the training loss look like, validation loss look like, accuracy F1, so on and so forth of the train and validation. So you can always see if your model is overfitted or not. Okay. So once finished training, so don't use 50 steps on the hackathon, all right? You're gonna need to train more than that on the competition day. So once we finish training, we can evaluate the model by using the trainer predict. Okay, so once you run this function, if you define these, if you also pass the classification matrix or kind of like compute matrix function when you define trainer, and when you call the predict function, the model automatically evaluates the result for you as well. So basically, you can just pass this evaluation function, predict the test set, and you got a test result. Okay, but some notes here. You won't get the test data on the hackathon. You are gonna get only the training data, and you're gonna need to split for the validation set yourself. And for the test data, you're gonna get only the text. You won't get the labels. You need to do the prediction and then format the prediction into the CSV, then upload it to the Kaggle. Okay, so if you run this predict function, you won't get any metrics here, because like we won't give you the labels, or else you can tune the best model with the test set, which isn't fair, right? Okay, so okay, the model is trained finish. There we call the predict function. Then we can get the model prediction results. So I won't go to the Wong Nai reviews here. It's generally most of them are the same with the white sites. So now that we have fine-tuned the encoder-based model for the text classification, let's move on to how could we do in context learning for text classification. Before I go, is there any question here? There's a lot of info to be packed within like this 15 minutes also. Okay.
So when you mentioned that we need to do the splitting and everything in the competition, right? I was wondering if that is the same part as the hackathon. So
okay, so you can actually don't split the validation, but it's going to be very hard for you to analyze whether your model is overfitted to the train set or not.
So my question was that in that case, like when we do the final pitching in the hackathon, do we necessarily is making your like local model mandatory?
You mean like, do we need to build a local model?
Yes.
Yes, because like, although there's kind of like many approaches to the track one, some do the data set, somehow we somehow evaluate if those data set or those data set actually works when training with the model, or actually we can use some kind of like in context learning or so on and so forth to make sure. So at some point we got to benchmark whether your approach is kind of like legit or not. Okay, so you feel free to do anything you want, but at the end, we want to make sure that it's actually provides some contribution to the model with some benchmark, right? Or else we can say like, oh, there's a lot of data set here is good, but how can we know that those data set actually contribute to something, right? Yeah, fair. All right, cool. Okay, so let's move on to the in-context learning for text classification. Anybody here hasn't finished downloading the 7 billion model? Well, how many percent have you finished? There are like 99 charts also. Are you at like chart 70 or 80? The last one, okay. Oh, okay. Okay, so I'll go through it briefly. So while you are loading the model, I'll tell you what does this function does to make sure that everyone's on the same page. Okay, so like previous workshop, right? The previous workshop, we mentioned that we use the auto model from pre-train, right? In this task for in-context learning, we use the decoder-based model, or sometimes we call causal LLM. Causal means that we predict word by word, right? And that's what in-context learning does as well. So we define the auto model of causal LLM and from the pre-trained model. So for this case, we use Wang-Chan GLM. It's not the base model, but there's definitely a better model out there. I encourage you to experiment with some different model, but make sure that you have I want some reminder that you have a very limited time. So make sure you utilize them properly. Okay, so we load the model, we freeze the model parameters, because like for in-context learning, we don't need to fine tune anything. So, all right, then we set the model into the evaluation mode and make sure that the number of vocab of the model and tokenizers are equal. We set the padding token to the left. Can anybody guess why instead of padding to the right, just like encoder, we padding the model to the left now? Can anybody here guess? Yeah, you can actually predict the next word if you pad everything to the right, right? It doesn't make sense. Okay, great. Okay, then we make some sanity check if the tokenizer and the model actually have the same vocab size. Then we load the model and tokenizers. Okay, so once we finish loading the model, we make sure that you actually use the CUDA runtime, or else you're gonna download everything again. Make sure you have a CUDA runtime. Okay. Okay, so again, download the data set. You can see here the same text here, and we map the labels from the code, the 0, 1, 2, 3 into the actual classes. I define this mapper from using the infos from the Hugging Face. So I convert all the 0, 1, 2, 3 into the class name, which is like positive, neutral, negative, and question. So at this point, your data set is going to be as follows. You have the type text and the category and the labels in a string format. Because like in context learning, they learn everything in a form string, right? So we need to format everything in a form of string, unlike the encoder-based model. Then we're crafting prompt. So for this case, we're going to use this prompt format. This prompt format is often called few-shot learning prompts, where we give the model some context. And this context, we're going to sample from training data. So some little bit of remark here. This is just an example prompt. You can actually experiment with different prompts from different models, and that's fine. This is not a perfect prompt, but it's good enough for using it as a workshop. And I want to note something. There's a lot of researchers show that, well, obviously, that if you provide more example, the model tends to perform better. But note that although it performs better, it consumes more sequence lengths, and thus it makes your prediction way slower. Okay, so some notes on these prompt design. You need to make a different version of trade-off. If you're doing the prompts that are to like comprehensively explain the model what to do, it could consume too much sequence length. And sometimes if the sequence length is too long, the models tend to perform worse. So a little bit of a remark on that. But who knows, you guys might craft some prompt that the model could work even though it's a long sequence. So let's see. Okay, So here I write some codes to generate the prompts. I define the get example where it randomly selects the example from the training set. And then we craft the prompt here. Here's an example. I create a prompt on the first test set data, and you can see here that this is the prompt for the models, and the model needs to predict the next word here after the prompt. Okay, so once I finish define the function for crafting the prompt, I create the test prompt using the function, and then we can see here that here's the example of the trace prompt that we generated. Okay, so here's the prompt, and here's the label. We expect the model to predict negative, right? But the next step here is that instead of preparing as a raw string, right? There's a problem if we feed this text directly to the causal model. Can anybody guess why? Yeah, this is a little bit tricky because like if you're doing ChatGPT, you can just copy this and paste and the ChatGPT is going to answer it correctly, right? But if you use an open source model, you can actually use some tweak to make sure that it's somehow customized towards this kind of task. So remember that causal language model is the task to predict the next word, right? And we see that Wangchang have up to around like 25K vocabulary. How can we make sure that the next word prediction is positive, negative, question, or neutral? How can you make sure that when the answer is not answer some random stuff, like for example, I don't know, because like it's not, we will not like constrain the model to predict some certain words, right? So the good thing about coding by not using ChatGPT is that you can actually constrain the model prediction to bias toward the vocabs that you just specified. So for this case, if you want to apply the in-context learning for text classification, you got to constrain the model prediction to only predict just 4 vocab. Okay, but that's a problem because like we don't know if the word positive, the model is going to tokenize to post and tive, right? But the good thing is that for Wangchang LM, we test by letting the model tokenize this for class name, and it's just one classes. So it's very easy. So we just feed the prompt into the model, and when the model returns the probability of the next token, we can just select only the index, only the logits of these 4 words. And then we can make sure that the model behaves exactly as you want. Okay, so this is the good thing about not using ChatGPT, but good luck finding the model that is better than ChatGPT. Okay. I didn't mean that there's no model that is better than ChatGPT. Llama 2 is kind of like better in some sense, but make sure you make some experiments towards this kind of stuff as well. Okay, so here I provide some info. So in case that you don't follow me, you can just open the Colab and read what I write. I make sure that everyone is kind of like, because I'm afraid that I can't put everything within this 1 hour. So in case you confused with anything, you can go and read my Colab here. Okay. Then we define the function to batch predict the model. Okay, so every time we iterate over each batch, we want to make sure that we have the sequence length of each batch at the maximum length so that we don't truncate any info, right? So we define the function to get max length of each batch. For example, we don't want the model to predict single prompts per time because like model can do batch inference. Sometimes we want the model to predict around like 8 or 4 samples per 1 forward. So when you're using more than 1 sample per batch, you gotta patch to make sure that these 2 samples have the same sequence length. And then we define the function to generate the output here. So it's simply just get the max length of each batch, tokenize the batch string into the encoded labels, and then move batch to the GPU. Then we forward the model to get the logits here. The function model that generates here predict the next word for the given batch. So you can get the probability of the next word from the given prompts. And then you select only the class that we want. So we get the logits from the output, right? Then when we apply the softmax here, we want to make sure that we apply the softmax of the label IDs that we just defined earlier. So the label IDs here is the index of the word positive, negative, question, and positive. So this way, the output probabilities contains only 4 vocabs that we wanted. Then we'll return the outputs here. Okay, let me run this code first. All right, then we start running this generation. I think I cannot run these codes because it took like 10 minutes or so, and we're going to be out of time before we go into the NER. So you can try run this at home. And then you can see the prediction here. So we sample the example from the training data, right? And then we provide the text from the test set, and then we let the model fill here. If we don't do the constraint prediction, the model answer ngong, which doesn't make any sense, right? So we want to help the model to predict something good by, let's say, constrain the word into this 4 vocab, and then we can get the probability of each vocab. So the good thing is that the model predicts it correctly. So this is a cherry pick example, by the way. So I actually ran the evaluation. So I reused the codes from the previous collab, and you can see that the accuracy was just 31%. It's not very impressive. But hey, we can improve. There's a lot of gaps to be improved, right? There's a lot of model to experiment. There's a lot of prompts to be explored. And there's even some techniques. So here, you're sampling the example for the model for few-shot learning, right? Actually, the sampling method also matters. Like, for example, if we can somehow sample the example so that the model can make a better prediction, then that's good. But make sure there's trade-off on everything, all right? So this is how we do in context learning for text classification and supervised fine-tuning. All right, so anybody here have some question? All right. So that's it for text classification, and I'll try to finish NER within 20 minutes. So bear with me. All right, I'm gonna go a little bit faster. So for NER, let's switch back to the supervised fine-tuning. NER is a task for identifying some important section in the text. Like, for example, if I have a paragraph, I'll download the dataset first. So here, let's look at the first dataset sample. We have a dataset called Thai NER here as a workshop. It's a PyThai NLP data. The text is ทักษิณชินวัตรทวีตไม่บอกแปลกใจศาลปกครองสูงสุด blah blah and whatever. Well, no political stuff related, but okay. So we can see here that ทักษิณชินวัตร is a person, right? We want to identify that these 3 tokens are actually person. So NER can be framed as token classification, where we predict each token whether it starts of the spans or not. All right, as simple as that. Then the next thing is that you can see here, I made some comprehensive explanation in case you can't follow me or I didn't finish it in time. Okay, so here you can see that the Thaksin is index 0, space is index 1, Shinawat index 2, so on and so forth, right? We want to predict the token of each index. So this is our X, this is our data. Our labels should be the same list length as the X. Like for example, for this case, we want to predict whether Thaksin is a person, space is also a person, Shinawat is also a person. As simple as that. This is how we tackle the NER case for encoder-based model. So let's look at the label that the model prepared. So there's actually some bugs in the data set. You can see here that the date is misspelling. So I didn't fix this because like I have no time to fix the data. But during the completion, it won't use the same data set. But make sure you investigate if there's any bugs in the code. Okay. So okay, there's some issue with annotating like this. If I say that I want to do the token prediction and I just like naively predict the class of each token, there's some issue if, for example, if I say I have the word Thaksin Shinawat and Jinglak Shinawat consecutively. There's an issue because like Thaksin Shinawat and Jinglak is kind of like different entities, right? And if you predict like, for example, person, you can actually distinguish the separation between Thaksin and Jinglak at all. So there's some kind of like an engineering. So instead of like predicting the class token, we have the beginning and in the word token, B and I. B indicates the start of the span, and I indicates the continue of the span. So this way, if we have B and I, we can make sure that although the span are consecutively annotated, the model can distinguish whether the consecutive span are actually from different one. Okay, and the unknown, like the token that we don't care is kind of like marked as old, or like we skip those tokens. Okay, so likewise we prepare the evaluation function. compared to the text classification, this function or class is the compute matrix function. We use the sequence evaluation from Hugging Face, so it automatically evaluates the performance of the NER model. All right, so first we define the benchmark function, then we initialize the model. So the good, like I said, the good thing about using the encoder-based model is Hugging Face do everything for you. You use the auto model for token classification, then you give the model names, number of labels, and the mapper of the class index. Then you get the model right away. Then we encode the data set, but this one is a little bit tricky because like you are not encoding the whole sentence, and for this time, once you tokenize the sentence, you need to make sure that the token label actually aligns with the vocab after you tokenize. Like for example, if I have the word, this is an example sentence, all right, and then each text here, we have index 0, 1.2, 1, 2, 3, and 4, right? Once I tokenize, it could be something like this. If I say that example sentence is one span, the label is 3 and 4. Once the model is tokenized, it's now this whole span here. So you need to somehow align the labels from word labels into subwords label after tokenize. The good thing is that Hugging Face also handle this thing to you as well. So when you tokenize the vocab, right, you can get the word index by getting the word IDs here. And then you realign everything. Then you get the tokenized data set here. I would encourage you to go through this code again at home to make sure that we're on the same page. But let me give you some example here. So before we align the token, you can see that the word Thaksin is index 0, space is 1, Shinawatra is 2, and so on and so forth, right? Once we align the token, you can see here that the start of the sentence is negative 100, meaning that we don't care this text because like it's special token. Thaksin, okay, so this one is start of the word Thaksin here. This one is the word Thaksin, space, and Shinawatra here. So you can see here that once I tokenize, the label is also corresponding to each subword instead of each token instead. Okay, so you can go try to play around and see how these dynamics work for this function. But the main goal is that we want to realign the token label into the subword label of each token. Okay. Okay, so once we are ready with the data set, we define the compute matrix function again by just calling the benchmark classes, and then we define the training arguments, padding function, the data collector, and trainer. Then you start training. As simple as that for the NER. Okay. Anybody here have some question on aligning token labels? It's a bit complicated. Okay, cool. So if you missed something or I'm going too fast, I encourage you to go each line. I make a lot of comments. I actually spend a lot of effort trying to add those comments and those explanations to make sure that you understand everything. But if you have some questions, feel free to ask me later on. Okay. When we start training, we use the same arguments there. And then I actually provide some code snippet on how to load the safe model. So it's actually just from pre-train and then point to the safe part here. Then you can actually load the models. Then you do the same as previous one. Okay, let's just keep this for now. We want to predict the test set. So this one is a little bit trickier because like we need to tokenize the train data. Let's the model predict the subword token and then realign back to the token level. So this code here, so you're doing the other way around when you inference, right? When you're training, you have the input data as an X in the token level and its corresponding label. You need to tokenize into subwords and then realign the label with the subwords, right? But when you're doing an inference, you are not given the labels. So you need to tokenize the text, get the labels on a subword labels, and then map back into the token label for the prediction. And these inference codes provide a snippet on how to predict the model. Oh, this one is actually the, yeah. So the good thing about NER is that when you're decoding, there's some info that you can leverage to make the prediction better. Like for example, if the models, here, let's go back to this example. If the model predicts as B person, the only next token is going to be B, I, and O person, right? It can be B person, then let's say I date, or so on and so forth. We can actually constrain the prediction of the model from B person into only I person or O or B person again. Okay, so this code here, when the model makes some prediction on every time step, we make sure that the models only transition into the possible next token. Because like we're using the BIO annotation scheme, right? If, let's say we start, I'll give you an example here. So during inference, the model predicts the probability, like for example, the word A, B, and C. The first label could be O. O can be followed by B, I, or O, right? But if you start with, let's say, B person, the only next token that you can predict is I person, B, any class, or O. So if you limit the probability logics of the model, you can make sure that the model won't behave something like B person, I date, for example. If we constrain the prediction of the model, we can make sure that the model doesn't make these mistakes. Okay, so this code snippet here on the collapse will define the inference class where it wraps the model tokenizers and the class 2 index mappers. Then during the prediction, it will go through each time step and then make sure that the decoding function is behaving according to the transition rules that I mentioned earlier. Okay, so the predict function here, model predict the probability logics, and then we make some decode function here. Then we run the prediction, then we get the NER results here. So again, I'll encourage you to go back and read this code and make sure we align on the same page, because like this is kind of like complicated stuff. In the worst case, you can just reuse my codes, but make sure you understand what I'm doing. Okay. Okay, so that's it with the supervised fine tuning. Then we're gonna do the in-context learning for NER. So this one is even more complex because you need to do the few shot example for the NER, right? We prepare the data set again, get the class 2 index here, declare the same benchmark function, prepare the model. Then for the in-context learning for NER, you can actually customize more prompt. There's a lot of prompt format that you can use for token classification. But for this one, I'm gonna use this kind of prompt where I give the example as the tokenized text delimited by the pipe. And then we let the model predict the corresponding labels. Okay, and when we feed the test text, we expected the model to fill those token labels. You do the same process just like in the text classification, where you define the prompt function, generate some samples. I use the delimiter token as a pipe. You can use anything you want. Then let's investigate the prompt here. You can see here that once I finish crafting prompt, you can see here that here's the prompt and here's the expected labels to the model. All right. Then we prepare the class index, because just like text classification, we gotta get the class, the vocabulary index of the labels of each token, right? We make sure that we get the token labels here, define the function, then we can see that the algo was tokenized to the AGO alone. The email was tokenized to E and mail, so on and so forth. It's more trickier because right now we don't have a single vocab for each class. And it's a pain in the whatever, because like you need to make sure you define the actual transition function correctly. So I define this tokenized index first. The special tokens ID is kind of like the tokens that we want for utilizing the NER function. And the words here is the input. We craft the prompt from the inputs. Okay, so The challenge thing is that here I make some simplified state transition function here. So we want the LLM to decode by constraining the prediction following this kind of flow, right? We start with the model prediction from the context, right? The models are only able to predict either B or O. Because like for the first word here, the model needs to predict whether it's the start of span or it's not a span, or it's not an entity, right? If it's start of an entity, then we autofill with the dash commas to let the model predict what class is it beginning with, a Go data or whatever. Then we can autofill this later. But the problem is that if the word start with per, it can be percent or person. You need to handle this case as well, right? Now it's gonna be more tricky if you have a very similar, let's say class name. You can actually do some simple hack by changing the word person into human or something to make the prompts more simplified. But for this, I want to give you an example of what to do if we have some complicated prompts here. You need to handle everything. If you can define this perfectly, then you could be doing the in-context learning prompt. It's like if you define this state transition function correctly, then you can just define the state transition function, let the model predict the next words, constrain the prediction to those predefined function, and then repeat the same process all over again. Okay. I give you some example for decoding. This one is hell of a complicated code. I encourage you to go and play with this everything, but I make the function very like verbose. I make a lot of comment on how the things are transition, so on and so forth. And then I'll give you some demo on what happened if I run this code. So here you can see, no, that's this one. Okay. Okay, so this is the input. Okay. The model is predicting the first step. So the model is only available to predict B or O, right? And then here's the logic. After we select only B or O, then we Rmax, we get that the first word is O. Then when the first word is O, we can auto-complete with a word delimiter token, and then we update the next possible state. If the model predicts O, the only next possible position is either B or O, right? Then you can see that the model predicts O. Then for the second step here, we repeat the same process over and over again. We can see that the model actually predicts just O. So have some remark that this is not a perfect prompt. If I were you, I will craft new kind of prompts. There's actually a lot of ways to prompt this model. So for example, this is not a very good prompt because like we can ensure that the model retrieve the correct word position from this way. You can kind of like say 9 O, then ประกอบ O, and then lat O, space O, desha O. That could be a better prompt, right? Not just like 9 desha lat and then O, and so on and so forth. You can make the model predict each token by seeing each tokenized word. That's going to be a lot better, but I encourage you to try with different prompts. Okay. Some remark here. If I sample some new, let's say, new context here. If I have the context like พลตำรวจโท สันเจริญ so on, we can see that, and let the model it predicts stuff again. The model actually predicts the first one as a person. So context actually matters a lot here. So make sure you do some algorithm to provide some context. Engineer some new prompts. Define the state transition function correctly, and then craft the in-context learning decoder. So use this as an example for how we can apply the decode function. Okay, so once we finish, we use this course. I increase the number of examples into 2, and then I reiterate over the whole test data sets. So it takes forever because like the model needs to predict a single words, right? And if the sequence is like, let's say, for example, 200, so the model should predict 200 words. But some remark here, you can actually expand more example for more than 2, because like all else, the sequence length is going to explode. But if you have access to A100 for AWS, right, you can actually increase the context length, but make sure that your pre-trained model or like the LLM that you're using are good for long context as well. There's a lot of papers saying that the model tends to behave weirdly when the model predicts the sequence length longer than your pre-trained. So make sure you keep that in mind. There's a lot of trade-off to do. Okay, so and then we evaluate the results using the benchmark function, and that's it for using in-context learning for any text classification. So the key concept here that I want you guys to actually spending time on is the in-context learning. If you are doing the track one and you are doing the large language model, or maybe you might consider switching to encoders, I don't know, but yeah, it's a good try for you to, the key concept for in-context learning is that define state transition function correctly, predicts the model, prove the probabilities, then do the constraint prediction, then that way the model can behave way better than you could probably imagine. Okay, so that's all for the workshop. I can't believe I finished everything in 1 hour. But okay, I encourage you guys to actually read more on what I was coding. If you have some questions, feel free to contact me via Twitter. So you can DM me here. Any question is welcome. I genuinely actually wanted you to ask some question if you have some, actually get stuck with those codes. Okay.
All right. Thank you so much,ครับ. A big round of applause. โอเคมีท่านไหนอยากถามคำถามไหมครับไม่มี
This is like a university lecture.
All right.ก็โอเค normally if you have a question, feel free to contact him with X account. All right.
Okay. Thanks.
All right.